Everyone, hope you're having a great day. Let's check out class number 25, where our goal is to calculate the force of gravity acting on an object. Let's see, graph weight versus mass as well. Okay, cool. So the camper slides down a water slide, but he forgot there's no water running down it. Oh no. Gravity pulls him down the slide with the force of, let's see. So gravity is pulling him down with the force of 310 newtons, but the frictional force points in the opposite direction of his body's motion, and it is 130 newtons. If the boy has a mass of 50 kilograms, m equals 50 kilograms, what is his acceleration down the incline? So you have to choose one direction to be positive, one to be negative. Doesn't really matter. I will make up the incline negative, right? So up the water slide negative. So we're going to use the equation A equals F net over M. All right, and I'm going to plug in, let's see, F net. So F net, you just go to the free body diagram and put in those two forces. So 310 plus negative 130 divided by the mass, which is 50. Throw that all in your calculator. Let's see what we get. We get 180 divided by 50. We get 3.6 meters per second squared. All right, so grocery bag dilemma. We just spoke about ripping grocery bags and how if you accelerate them upward too quickly, the force you have to apply to do that rips the grocery bag, so don't do that. All right, so force of gravity. Weight is the force of gravity acting on an object. It is measured in newtons. Okay, it's a force. It's a force of gravity, and it changes from planet to planet. On Earth, for example, I have a weight of, let's say, I don't know, 1,000 newtons. But on the moon, I have a different weight. Okay, your weight, in regular units that you use it's pounds. Like if you stand on a scale on Earth, it reads like, let's say, 200 pounds. If you stand on the same scale on like Mars or on the moon, it's going to be a much different number. Okay, now mass is different than weight. Mass is the amount of matter making up an object. It's how many molecules make you up. You learned in chemistry that, if you have 6.022 times 10 to the 23rd molecules of carbon, that is going to have a mass of 12 grams. It's dependent on the amount of material, okay? That's measured in kilograms. These are two different things you have to be very careful. And mass does not change from planet to planet. My mass, the number of molecules that make up my body, does not change from planet to planet. All right. So the formula for weight given on the reference table looks something like this. Little g equals Fg over m. Okay, little g is the acceleration due to gravity. Fg is weight, or force of gravity. And m is mass. And again, g is acceleration due to gravity. I will never write it like this, though. I'm going to write it one of two ways. I will either write Fg equals mg, or weight equals mg. Those are interchangeable. Okay? So again, Fg represents weight, or force of gravity. M is mass, make sure it's in kilograms, and little g is the acceleration due to gravity. On Earth, that number is generally 9.8. It is 9.8 on Earth, but on other planets, it's different. So 5, make sure you always make g equal to 9.8 meters per second squared for this. Again, on Earth. On Earth. We might not always be dealing with Earth. Mass must be in kilograms for this one. So what is the weight or force of gravity of a 26 kilogram rock? So weight equals mass times gravity. I'll just write it out for the first time. M times g. So 26 kilograms times 9.8 meters per second squared. Let's see, 26 times 9.8. We get 255 newtons, right? Because that's the unit for weight. Weight is a force. So this question on the right says, how would the mass and weight of an object on the moon compared to the mass and weight of an object on Earth? Well, we know the masses are going to be the same, but the weights will be different. Okay, so it says the mass and weight would both be less. No, because the mass is going to be the same. It's like the mass would be the same, but the weight would be less. That is the answer, but let's look at the other ones. The mass would be less. No, mass is going to be the same. And it's saying here that mass and weight would be the same. Well, we know mass is the same, but weight is not the same. Weight changes from planet to planet. All right. So the same rock is now on the moon. The acceleration due to gravity on the moon is 1.6 meters per second squared. What is the mass of the rock on the moon? What is the weight of the rock on the moon? So we know that mass does not change. So this is 26 kilograms. And now weight, well, weight is equal to mg. But watch out, okay? A lot of people are going to make G accidentally equal to 9.8, right? G, that's a bad G. G does not equal 9.8 here because we're on a different planet, in this case, the moon. The moon's not a planet, but you get the idea. 1.6 meters per second squared. So we have 26 kilograms, 1.6 meters per second squared. And let's see, 26 times 1.6. We get 41.6 newtons. Okay, think about that. Compare that to the weight on Earth. Okay, on Earth, this thing weighs 255 newtons. On the moon, it weighs 41.6 newtons. Now, don't worry about what a newton is exactly. I mean, a newton is about, or let's say, newton is about, I don't know, like, a small amount of mass. I'm like blanking right now. Um, a newton's not a lot of weight, rather. But think about how much smaller it is. 41 over 255, that's like a fifth. Okay, less than a fifth. The mass, all right? It's like a sixth the mass, or the weight. I keep saying mass. Yeah, even I make the mistake. Notice how weight is not the same as mass. All right, so let's just practice some free body diagram stuff real quick. All right, so we have a 5 kilogram medicine ball, and it falls from a shelf. So here's my free body diagram. The only force acting on it is its weight. Now you can make the weight negative here, but I'm going to just make it positive because there's no upward force, so I'll just make downward positive. Okay, so the weight is the only force acting on it. So if I do A equals F net over M, my acceleration is what I'm looking for. You should know the acceleration of a falling object, right? We know the answer is going to be 9.8, but let's prove it. Now, F net is going to be replaced by the forces in our free body diagram, so we're just going to replace it with weight over mass. So A equals, what's our weight equation again? I think it's equal to mg. So we're going to place weight with mg over m. Masses cancel, and I get that the acceleration is equal to g. 9.8 meters per second squared. Look at that. This actually kind of proves why the acceleration due to gravity is independent of mass. Okay, look at that. Weight is dependent on mass, and weight divided by mass, well, masses cancel. So masses cancel out. So mathematically, that is why the acceleration due to gravity is not dependent on the mass of the object. This one's a little bit more complicated, but it's the same basic steps. A grocery bag can withstand a force of 250 newtons without ripping. The bag is overfilled with groceries, 20 kilograms worth, and is accelerated upward at 5 meters per second squared. Does it rip? So 250 newtons is not the upward force. We're looking for the upward force, and then we're going to determine, does it rip? So here's our groceries. Okay, the weight going down, negative weight. And we have the force of the bag going up. We'll call it F bag. The reason I made weight negative this time is because there is an upward force. Like, you have to make one of them negative if you have forces going in different directions. All right. Now, what is my weight equal to? It's equal to mg, right? So mg, so it's equal to negative. M is 20. G is 9.8. So I'm not going to write that out, but you should be writing it out. So the weight comes out to be negative 196 newtons. All right. That's an important thing. Okay. So here is my weight. So I'm going to do A equals F net over M. A is 5. F net, I just go to my free body diagram and write each of the forces. So I have the force of the bag, that's positive. Plus, now you're not going to write all three of these weights down here. You're just going to write one of them. So I'm going to write negative 196 newtons. All right, and then my mass is 20 kilograms. All right. Cross multiply, I get 100 newtons equals F bag minus 196. So the force on the bag is going to be 296 newtons. By the way, this shouldn't have said acceleration. This should have said, does it rip? All right, F bag. There. Okay, so does it rip? Let's see. The force of it. Yeah, it does. It's more than 250. 296 greater than 250. So it rips. All right. Let's look at this last bit here. This was mostly for homework. It says create a weight versus mass graph using the data below. This is on Earth. Okay, this is on Earth, so we know G is equal to 9.8. So to get the weight from the mass, you simply multiply by 9.8. So 0 times 9.8 is 0. Let's see, 3 times 9.8 is 29.4. This is 49. Just do these all on your own. 98, 196. I can't do that one in my head though. 8 times 9.8. 780, or excuse me, 78.4. And let's see, that's going to be 147. I think that's what it is. Okay, just kind of guess there, but I think that's right. Okay, so weight versus mass. So you have to do a few things here. You have to do weight versus mass. You have to give it a title. Okay, hold on, I'm freezing up for half a sec. All right. So on the y-axis, we have weight. Don't forget to put the units there. That is important, newtons. On the x-axis, we have mass, and that's in kilograms. All right. So let's see. We go 0. We have 0 here, and then on the mass, we go up to 20. So each box can be like 2. So 0, 4, 8, 12, 16, 20. Then let's see, our greatest, let's go weight up to 200. So each box is going to be 20. So we'll go 40, 80, 120, 160, and 200. All right. And then you're going to plot your data and you're going to get some sort of slope. Great. Find the slope or draw the slope, line of best fit. You have to have a line of best fit. So find the slope, show the work below. So when you do the slope, you should do slope equals rise over run. Don't use your data points, please. You don't know if your data is perfect. In this case, it is perfect, but you don't know if it's always going to be perfect. So you have to do rise over run using your data points. So you have to do like rise, run, that whole thing. Okay, rise, run. You have to do it this way. Don't do y2 minus y1. We don't do that in this class. All right. So in doing that, you should get, hopefully exactly, but close to 9.8. And then the units are always y unit divided by x unit, newtons per kilogram. Now, what is that 9.8? That number should look familiar. It's 9.8 meters per second squared. Now, I know what you're thinking. How the heck is that meters per second squared? Well, we've said this before. A newton is equal to a kilogram times a meter per second squared. If I divide both sides by kilograms, I have newtons over kilograms equal meters per second squared. There it is. So what does the slope of a weight versus mass graph represent? It represents the acceleration due to gravity on that planet. All right. So there we have it. If you have any questions, let me know. There was class 25.